Right now, building a single reliable quantum computer could require more physical qubits than there are stars visible to the naked eye. That's the problem that has haunted physicists for 3 decades. And in 2026 alone, researchers at the University of Chicago have proposed 3 completely different ways to make that problem disappear. Let's slow down for a second, because that number is not an exaggeration. On a clear night, away from city lights, the average person can see somewhere between 2,000 and 3,000 stars with the naked eye. Some early designs for fault-tolerant quantum computers estimated that you would need millions of physical qubits working together just to produce a single, reliable logical qubit. Millions, not thousands, millions. That's the scale of the wall that quantum computing has been running into for years. Every time scientists get closer to building a machine that can actually outperform a classical computer on a useful, real-world task, this wall of overhead shows back up. You need more qubits. You need more error correction. You need more control hardware, more lasers, more magnetic fields, more everything. And the deeper you dig into the engineering, the more it starts to feel like chasing a horizon that keeps moving further away. So when a single university starts putting out breakthrough after breakthrough, all aimed at shrinking that wall, people notice. And in the case of the University of Chicago, it hasn't just been one lucky paper. It's been 3, each tackling the problem from a completely different angle, each landing in a serious peer-reviewed journal, and each claiming to remove a piece of the overhead that has made quantum computing so brutally expensive to scale. To understand why this matters, you first need to understand what a qubit actually is, and why quantum computers are so fragile in the first place. A classical computer, the kind sitting in your pocket or on your desk right now, stores information as bits. Each bit is either a 0 or a 1. Simple, stable, reliable. You can flip a bit, copy it, store it for years, and it stays exactly what it is. A quantum bit, or qubit, is different. Instead of being locked into a 0 or a 1, a qubit can exist in a state that is a combination of both at the same time. Physicists call this superposition. It's part of what gives quantum computers their theoretical power. Instead of processing possibilities one at a time, a quantum computer can, in a sense, explore many possibilities simultaneously. But that power comes at a brutal cost. Qubits are almost unbelievably fragile. The same quantum properties that make them powerful also make them incredibly sensitive to their environment. A stray vibration, a tiny fluctuation in temperature, a stray photon bouncing off a nearby wall, any of these can collapse a qubit's delicate state and destroy the information it was holding. Physicists call this decoherence, and it is, without exaggeration, the single biggest obstacle standing between quantum computing as a laboratory curiosity and quantum computing as a tool that can actually change medicine, cryptography, and material science. Classical computers deal with errors using redundancy. If a bit might be corrupted, you just copy it several times and take a majority vote. Simple. But you cannot do that with a qubit. There's a fundamental law of quantum mechanics called the no-cloning theorem, and it says exactly what it sounds like. You cannot make a perfect copy of an unknown quantum state. It's not a technological limitation that better engineering will eventually solve. It's a hard law of physics. So instead of copying information directly, quantum engineers have had to come up with far more elaborate ways to protect quantum information from the chaos of the outside world. The most common approach for years has been something called a surface code. Picture a large 2-dimensional grid of physical qubits. Instead of storing one logical piece of information in one physical qubit, you spread that same logical information across dozens, hundreds, sometimes thousands of physical qubits arranged in this grid. By constantly comparing neighboring qubits to each other, you can detect when something has gone wrong without ever directly measuring the fragile quantum state itself, which would destroy it. If 2 neighboring qubits disagree in a specific pattern, that tells you an error occurred somewhere nearby and you can correct for it. It's a clever trick, and it works. The problem is the overhead. Surface codes are incredibly wasteful in terms of resources. Some estimates put the requirement at somewhere around 1,000 physical qubits for every single reliable logical qubit. If you want a quantum computer that can run algorithms complex enough to be useful for things like drug discovery or breaking modern encryption, you would need so many physical qubits that building the machine becomes almost absurdly expensive and complicated. This is exactly the wall that the first of the 3 University of Chicago breakthroughs went after. A team at the university's Pritzker School of Molecular Engineering, working alongside researchers from Harvard, Caltech, the University of Arizona, and the quantum computing company Quira, proposed an entirely new blueprint for error correction. Instead of relying on the traditional surface code, they built their approach around something called quantum low-density parity check codes, or qLDPC codes for short. These codes had been theorized for years, but nobody had actually turned them into a realistic, buildable blueprint for a quantum computer. The Chicago-led team did exactly that. The trick wasn't just mathematical. It also involved new hardware. Specifically, they used reconfigurable atom arrays, made up of individual neutral atoms that can be physically moved around using precisely controlled beams of laser light. In a traditional grid-based surface code, each qubit can only really talk to its nearest neighbors, the ones directly next to it in the grid. That limitation is part of why the overhead is so massive. But by using movable atoms, the Chicago team's system allowed qubits to connect with a much wider range of other qubits, not just their immediate neighbors. That flexibility let them encode the same error-correcting information using dramatically fewer physical qubits. The headline number from that research was striking. Instead of needing something like 1,000 physical qubits per logical qubit, the new blueprint suggested you might only need a fraction of that, cutting the resource requirement by what researchers estimated could be a factor of 10 to 20. Instead of needing millions of physical qubits for a genuinely useful large-scale quantum computer, this approach could bring that number down into the tens of thousands. That's still an enormous engineering challenge, to be clear. Nobody has built a machine at that scale yet. But it moved the target from something that felt almost like science fiction into something that starts to look like an actual achievable engineering roadmap. That was breakthrough number one. And if that had been the only headline out of Chicago in 2026, it would already have been a big deal. But then, just weeks later, a completely different team at the same university, working on a completely different piece of the puzzle, published another result that again used the word shortcut. Oh, this second breakthrough had nothing to do with error correction. It was about entanglement, which is arguably the single most important resource in all of quantum technology. Entanglement is that strange phenomenon where two or more particles become so deeply linked that measuring one instantly tells you something about the other, no matter how far apart they are. It's the property that underlies quantum sensing, quantum communication, and quantum computing itself. Without highly entangled states, none of the promised advantages of quantum technology are possible. The problem is that generating rich, complex, highly entangled states in a laboratory has traditionally required incredibly elaborate setups. You need finely tuned lasers, precisely engineered optical cavities, and a whole toolkit of specialized hardware, much of it custom built for a specific experiment. It's slow, it's expensive, and it doesn't scale easily. A team at UChicago's Pritzker School of Molecular Engineering, led by physicist Ashish Clerk, found a way around a big chunk of that complexity. And the method they landed on is almost disarmingly simple once you understand it. In a typical setup, you have a group of atoms sitting inside an optical cavity, all interacting with light in essentially the same way. They're symmetric, indistinguishable from one another as far as the physics is concerned. That symmetry, it turns out, is exactly what limits the variety of entangled states you can create. If every atom behaves identically, you're stuck with a fairly narrow range of possible outcomes. The Chicago team's insight was to deliberately break that symmetry, not by adding new physical components, but by making small adjustments to the energy levels of different groups of atoms. Using extra lasers or magnetic fields, they shifted the excited state energy of specific atoms relative to one another, pairing them up so that each atom had a partner with an equal but opposite energy offset. That small tweak changes everything. Suddenly, instead of a uniform crowd of identical atoms, you have a system with built-in structure and individuality while still remaining fully controllable. By adjusting these energy offsets, researchers found they could dial in a surprisingly wide variety of highly entangled states that would normally require much more elaborate hardware to produce. And because the underlying tools, lasers, magnetic fields, optical cavities are already common in quantum physics laboratories around the world, this isn't some exotic setup that only one lab on Earth can replicate. It's something that could plausibly be picked up and used by other research groups relatively quickly. The applications reach beyond quantum computing too. Highly entangled states like these are central to ultra-precise sensing technology, the kind that could one day be used for things like detecting gravitational waves with greater sensitivity or building next-generation navigation systems that don't rely on satellites. So this second Chicago shortcut wasn't just a nice theoretical trick. It was a genuinely practical simplification of one of the most resource-intensive parts of quantum experimentation. Now, at this point, you might already be noticing a theme. Two different breakthroughs from two different research groups tackling two completely different problems, both published within about a month of each other, both out of the same university, and both explicitly framed by the researchers and by outside coverage as a kind of shortcut around a long-standing bottleneck. If that were where the story ended, it would already be a fairly remarkable coincidence. But then came the third one. This third breakthrough might be the most conceptually wild of the bunch, because it doesn't just try to make existing quantum error correction more efficient. It proposes a way to potentially sidestep one of the most expensive parts of the entire fault-tolerant quantum computing pipeline altogether. Published in the journal Nature in the middle of July 2026, this research came from a team that included UChicago's Ruben Verison, working alongside partner institutions, and the quantum computing company Quantinuum. The subject of this paper is something called non-Abelian anyones. If that phrase sounds intimidating, that's because the physics behind it genuinely is exotic. In our everyday three-dimensional world, particles are generally classified into two broad types, bosons and fermions. But in certain two-dimensional systems, physicists have long predicted the existence of a third category of particle-like excitations called anyons, and a special subclass of them called non-Abelian anyons. What makes non-Abelian anyons so strange and so useful is what happens when you move them around each other. If you take two of these anyons and swap their positions, physically braid them around one another in a specific pattern, the quantum state of the system doesn't just pick up a simple phase, the way it would with ordinary particles. Instead, the entire state can transform in a much richer, more complex way, one that depends on the exact path the particles took as they moved around each other. That braiding behavior is the key to everything, because the outcome depends on the topology of the path, the order and pattern in which the particles moved, rather than on the precise, fragile details of their exact positions at every instant. These braided states are inherently more resistant to small local disturbances. A tiny vibration or stray field might nudge a particle slightly off course, but as long as the overall braiding pattern stays intact, the encoded quantum information remains protected. This is the foundational idea behind what's called topological quantum computing, an idea that has been discussed theoretically for decades, but has been notoriously difficult to demonstrate convincingly in the lab. What the Chicago-linked team showed is that by braiding and fusing these non-Abelian anyons on real quantum hardware, they could perform a universal set of quantum operations. In plain terms, that means if you store information in these anyons and move them around each other in the right patterns, you can carry out any computation a quantum computer might need to perform. That's a big claim, and it's an even bigger deal when you consider what it might allow researchers to skip. Currently, most leading approaches to fault-tolerant quantum computing rely on a process called magic state distillation. Without getting lost in the technical weeds, magic state distillation is an extremely resource-intensive procedure required to perform certain essential quantum operations reliably. It's a bit like needing a massive, expensive purification process just to get a small amount of a critical ingredient pure enough to use. It works, but it eats up enormous amounts of computational overhead, adding yet another layer to the already staggering resource requirements of building a useful quantum computer. The promise of the anyon-based approach is that it might allow certain fault-tolerant computations to be performed without leaning so heavily on magic state distillation. One researcher involved in the related Quantinuum collaboration described non-Abelian codes as something of a dark horse in the race toward practical quantum error correction, and this new demonstration suggests that dark horse might be closer to the front of the pack than most people expected. To be clear, this is still described by the researchers themselves as a proof of concept, not a finished, scaled-up quantum computer, sitting in a lab ready to solve real-world problems tomorrow. But proving that a universal gate set can actually be implemented through braiding on real hardware is a serious milestone, the kind of result that shifts an idea from theoretical curiosity to viable engineering direction. So, there you have it. 3 separate breakthroughs, 3 completely different subfields of quantum physics, all connected to the University of Chicago, all landing within a matter of months of each other in 2026. The first tackled the overhead of error correction directly, using new codes and reconfigurable atom hardware to shrink the number of physical qubits needed by a factor of 10 to 20. The second tackled the challenge of generating rich, useful entangled states, showing that you don't need exotic new hardware, just a clever rearrangement of existing tools to unlock a much wider range of quantum states. The third went after one of the most expensive procedural bottlenecks in fault-tolerant computing itself, using the strange topological properties of non-Abelian anyons to potentially bypass a huge chunk of overhead altogether. Now here's the honest, important caveat, because it would be irresponsible not to mention it. These 3 results did not come from the same lab, the same research group, or even the same building on campus. They came from different teams, studying different physical systems, publishing in different journals, and pursuing different long-term strategies for how a fault-tolerant quantum computer might eventually be built. In that sense, calling this a single continuous streak as if one group at Chicago is on some kind of hot hand run would be stretching the story a bit further than the facts actually support. Science journalism, and especially science content built for social media and video platforms, has a well-documented tendency to string together separate, unrelated results into a tidy narrative, because tidy narratives get more attention than the messy, decentralized reality of how research actually happens. But here's the thing. Even once you strip away the exaggerated framing, there's still something genuinely interesting left underneath. The University of Chicago isn't randomly stumbling into quantum breakthroughs. It has spent well over a decade deliberately building one of the most concentrated quantum research ecosystems in the world. The university sits at the center of the Chicago Quantum Exchange, a hub that connects with two of the Department of Energy's National Quantum Information Science Research Centers, hosted at nearby Argonne National Laboratory and Fermilab. Back in 2020, Argonne and the University of Chicago built a 52-mile quantum communication loop, an early piece of infrastructure aimed at eventually supporting a functioning quantum internet. In terms of institutional rankings, the university was ranked as the top institution in the country and 6th in the world for quantum physics research output in a major Nature Index ranking. That's not the kind of ranking you get from a single lucky year. That's the kind of ranking that reflects a genuinely enormous, sustained concentration of talent, funding, and infrastructure built up deliberately over a very long period of time. So while it's probably not accurate to say the University of Chicago has cracked some unified secret to quantum computing, or that there's a single hidden thread connecting all three of these papers, it is accurate to say something more nuanced and, honestly, more interesting. When you build an environment with this much concentrated expertise across error correction, quantum optics, condensed matter physics, and materials science, all clustered together, collaborating with elite partner institutions and companies, you dramatically increase the odds that multiple independent breakthroughs will emerge in a short window of time. It's less like one lucky lightning strike and more like a properly wired storm system, primed to produce lightning regularly, just not always from the exact same cloud. Let's step back and think about why any of this actually matters beyond the walls of a physics department. Quantum computing, if it ever reaches the scale researchers are hoping for, isn't just an academic curiosity. It has the potential to reshape entire industries. In medicine, quantum computers could simulate molecular interactions with a level of precision that classical computers simply cannot achieve, potentially accelerating the discovery of new drugs and materials by years or even decades. In cryptography, sufficiently powerful quantum computers could eventually break many of the encryption systems that currently protect financial transactions, private communications, and national security infrastructure, which is exactly why there's now a global race to develop post-quantum cryptography. Encryption methods designed to resist attacks from quantum machines before those machines even exist at scale. In materials science, quantum simulation could help researchers design new superconductors, more efficient batteries, or entirely new classes of materials that don't currently exist in nature. And in artificial intelligence, some researchers believe quantum computing could eventually accelerate certain types of machine learning tasks that are currently bottlenecked by classical hardware limitations. None of that happens, though, if the fundamental engineering problem of building a stable, scalable quantum computer never gets solved. That's why breakthroughs like these three matter so much, even in their early proof-of-concept stages. Reducing the qubit overhead needed for error correction, simplifying the process of generating useful entangled states, and finding new physical systems that are inherently more resistant to noise. These aren't flashy, headline-grabbing demonstrations of quantum supremacy. They're the unglamorous, foundational engineering work that has to happen before quantum computing can move from research labs into anything resembling real-world deployment. It's less like inventing the light bulb and more like quietly redesigning the electrical grid that will eventually power an entire city's worth of light bulbs. It's also worth remembering just how young this field still is relative to where it's trying to go. The theoretical foundations of quantum computing stretch back to the 1980s and 90s, but the kind of experimental progress we're seeing now, actual demonstrations of error correction working as theory predicted, actual hardware capable of manipulating exotic particles like non-Abelian anyones, actual blueprints for scaling qubit counts down rather than up, most of that has only become possible in the last few years. Between late 2024 and early 2026 alone, multiple independent research teams around the world, not just at Chicago, crossed meaningful experimental milestones in quantum error correction, moving it from a purely theoretical requirement that everyone agreed was necessary into something that has now actually been demonstrated to work the way the underlying theory always predicted. That's a genuinely significant inflection point for the field as a whole, and the University of Chicago's cluster of 2026 breakthroughs is best understood as part of that broader wave, rather than as an isolated phenomenon happening in a vacuum. So, is this a pattern? In the strict sense of one team following one continuous thread of discovery, probably not. But in the broader sense of a research ecosystem reaching a kind of critical mass, where enough talent, funding, and infrastructure has been concentrated in one place for long enough that multiple independent breakthroughs start emerging in overlapping windows of time. Yes, that pattern is very real, and it's worth paying attention to. Chicago isn't the only place this is happening. Teams at other institutions and companies around the world are chasing the exact same wall from their own angles, using their own approaches, and some of them are making real progress too. But right now, in the middle of 2026, it's the University of Chicago's name that keeps showing up again and again, attached to a series of results that each chip away at a different piece of what has long been considered one of the hardest engineering problems humanity has ever taken on. Whether any single one of these three approaches, the qLDPC error correction blueprint, the reconfigurable entanglement method, or the non-Abelian any-on gate demonstration, ends up being the one that actually gets scaled into a functioning, commercially useful quantum computer, is still an open question. It's entirely possible that none of them individually wins out, and that the eventual solution ends up being some hybrid approach that borrows ideas from all three, along with contributions from research groups elsewhere in the world. That's often how major technological breakthroughs actually happen in practice, not through one single triumphant discovery, but through years of parallel, overlapping progress, made by many different teams, each solving a different piece of the puzzle, until eventually those pieces start fitting together into something genuinely transformative. There's another angle worth sitting with for a moment, and it has less to do with physics and more to do with how science actually gets funded and sustained over time. Building the kind of ecosystem that produces three unrelated breakthroughs in a single stretch of months doesn't happen by accident, and it doesn't happen cheaply. It requires sustained government investment through agencies like the Department of Energy. It requires long-term partnerships with national laboratories, and it requires universities willing to bet on hiring and retaining talent across multiple, seemingly unrelated subfields of physics and engineering, sometimes for years before any of that investment produces a headline-worthy result. From the outside, all anyone sees is the finished paper, the press release, the video breaking down the breakthrough. What gets missed is everything underneath it. The failed experiments, the years of incremental groundwork, the graduate students running the same measurement for the 100th time, trying to shave off a little more noise. That invisible layer is what a research ecosystem like this one is really built on, worth remembering the next time a flashy headline makes discovery sound easy or inevitable. It's slow, expensive, and unglamorous right up until occasionally it isn't. For now, what we can say with confidence is this: the overhead that has kept quantum computing locked in research labs for decades is finally starting to shrink, for multiple directions at once. Fewer physical qubits needed per logical qubit, simpler methods for generating the entangled states that make quantum technology powerful in the first place, and entirely new physical systems, like braided anyons, that might let engineers sidestep some of the most expensive procedural bottlenecks altogether. Individually, each of these is an incremental step. Together, especially when they emerge from the same institution within months of each other, they start to look like real momentum. Not proof that quantum computers are right around the corner, but solid evidence that the walls standing in the way are, piece by piece, starting to come down. And if that trend continues, whether it's coming out of Chicago or Cambridge or a lab somewhere else entirely, the timeline for quantum computing actually mattering in the real world might be shorter than most people currently assume.